Welcome to Chapter 5 of Surviving Statistics. In this chapter, we're going to talk about probability. Probability is the likelihood of something happening. For instance, what are the odds of you getting hit by lightning this year in the United States, or what are your odds of winning the lottery, assuming that you play it? Probability ranges from 0 to 1, and we usually represent it in percentages. So we could say that the probability could be 0% up to 100%. Sometimes we use odds, sometimes we use chances, sometimes we just simply use percentages. So some examples of probability might include the odds of flipping a coin and having it land on tails, the likelihood that your favorite college team is going to win the national championship this year, the odds of pulling a card at random and having it be a king of hearts, the chances of rolling a dice and having it come up 6, or the odds of you winning the lottery. Probability is extremely important in statistics, especially in inferential statistics. Remember, inferential statistics allow us to infer or make predictions about populations based on samples. So how this may actually work is maybe a new business is getting ready to introduce a new product, and so they've sampled people and they want to determine through inferential statistics and probability what percentage of people will buy their new product. Perhaps an epidemiologist is estimating what percentage of people will become infected with a new virus using probability and inferential statistics. So probability is going to be based on experiments and outcomes. The experiment is the process that creates the outcome, such as tossing a coin or throwing some dice. The outcome is the result, such as landing on tails or getting infected with a virus or not. When we're working with statistics, there's 3 different ways of assigning or choosing what the probability will be. We have the classical, the relative frequency, sometimes called the empirical, and the subjective, and we'll explain this in the next few slides here. The first method of determining probability that we'll talk about is classical. And classical is where we have a set number of outcomes and all outcomes are equally possible. So for example, if you flip a coin, you know it's either going to be heads or tails. And if it's a fair coin, the possibility of a head or tail is exactly the same. The same thing is true with rolling a dice. If you roll a single die, you have a possibility of getting a 1, a 2, a 3, a 4, a 5, or 6. So we know the probability of the outcome even before the experiment begins. Next, we have relative frequency or empirical probability. And to determine probability with this method, we use existing knowledge or repeated experiments that we've done in the past. So, for example, let's assume that of the last 100 customers that came into the coffee shop, 60 of them ordered a large coffee. So, using that relative frequency, we could assume that the likelihood or the probability of the next person coming in and ordering a large coffee would be 60% based on relative frequency. Subjective probability is based on intuition, guesses, and hunches, and it really has very limited value in statistical research and analysis. However, it is still used. Subjective probability begins with gathering all the possible information you can and then just making a subjective guess about the odds of something occurring. For example, maybe before a professional football season begins, you gather all the information about your team, who they've traded, who they've brought in on the draft, and at that point you look at some of the other teams and you just simply determine what you think their chances of winning the Super Bowl is. All right, let's check your understanding with the different types of assigning probability. So let's assume we have a deck of 52 cards. They're face down on the table. You pull the top card. What are the odds of picking the Queen of Hearts from that top card? If you guessed that we were using the classical method to determine the probability, you're absolutely correct. We know the exact probability. There are 52 cards in a deck and only 1 Queen of Hearts, so the probability of that top card being the Queen of Hearts is 1 in 52. All right, let's try another one here. What method would we use to assign this probability? What are your chances of being struck by lightning in the United States this year? We determined the probability of you being hit by lightning this year in the United States by past information. And so we know that every year approximately 270 people are struck by lightning, and with the population of the U.S. being about 340 million, your chances would be 270 out of 340 million. And that's an example of relative frequency. Relative frequency is based on existing or past knowledge. Okay, let's try another one. What method would we use to assign this probability? It's the first time you've ever attended a horse race. Now, as the horses and their riders kind of are paraded in front of you, you really like the looks of one particular horse. Maybe it's the color, maybe it's the way it walks, but you think, okay, that horse looks good. I think it's got a pretty good chance of winning the race. Well, let's examine the facts. You're an amateur. You don't know anything about horses, and you simply guessed based on the appearance of the horse. This is an example, is a really bad example, of subjective probability. Well, as we progress with probability, we're going to be doing some math. We're going to be computing probabilities based on multiple things happening. And there are a few terms that we have to go over before we actually get into the math. And let's go over a couple of these. So we talked about already an experiment. An experiment is the process that generates the occurrence. It's like rolling a die, flipping a coin. The outcome is the result of the experiment. Again, a head, a tail, a 1, a 2, a 3 from rolling a die. An event is a collection of experiment outcomes. So for example, my event might be tossing a coin 6 times. All right, here's some additional important terms when we're going to be computing probabilities. Collectively exhaustive means that when an experiment is conducted, at least one of the possible outcomes must occur. For example, when you roll a die, you must get either a 1, a 2, a 3, a 4, a 5, or 6. So all of those outcomes become collectively exhaustive. Mutually exclusive means that one outcome precludes another outcome from happening. So for example, you can't roll a 2 and a 4 at the same time. 2 and 4 are mutually exclusive. Then we have independent events. And the occurrence of one outcome has no effect on the probability of another. So for example, if you roll a 1, that doesn't have any influence on the next value that you might get when you roll the dice. After rolling a 1, you're just as likely to roll a 1 again, or 2, or 3, or any other number, because those values are independent. Another useful tool in determining probability is the complement rule. When using the complement rule, we'll recall that the sum of all possible outcomes must equal 100% or 1. And so the complement rule allows us to assign a probability of an outcome by knowing the probability of that outcome not occurring. The complement rule tells us that the probability of one specific outcome is equal to 1 minus the probability of not that outcome. You can see how we represent this here. The probability of A is 1 minus the probability of not A. So for example, the probability of not drawing the Queen of Hearts off the top of the deck was 51 out of 52. So knowing that, we could then determine the probability of getting the Queen of Hearts. So the probability of drawing the Queen of Hearts is 1 minus the probability of not getting the Queen of Hearts, or 1 minus 51 over 52, or 1 in 52. Of course, we have to get into some math because this is a stats course. Well, we're going to be talking about rules of addition first, and the first rule of addition we're going to be talking about is for mutually exclusive events. Remember, a mutually exclusive event does not preclude another event from happening. And our example is if we roll a 1 on a die, that doesn't prevent us from getting a 3 the next time. So if we're trying to find the probability of either or those events, in other words, two probabilities, we're going to add the two probabilities together. So let's use that example of rolling a die and getting either a 1 or a 3. We express that as the probability of A or B equates to the probability of A plus the probability of B. So if the probability of getting a 1 is 1 out of 6, and the probability of getting a 3 is 1 out of 6, we add the two together. So the probability of a 1 or a 3 is 1 out of 6 plus 1 out of 6 equaling 1 out of 3. Not all outcomes are mutually exclusive. Sometimes we can have one and the other outcome. And a good example would be, let's assume that we survey everyone in your city, so that would be a population, and we ask them, do you own a dog, a cat, or neither one? Well, as you can see with the Venn diagram here, we found that 25% owned dogs and 20% owned cats. However, we see that there's an intersection of 5% that own both. So these are not mutually exclusive. Owning a cat does not prevent us from also having a dog. So we compute the probability of either a cat or a dog in this example a little bit differently than we would for mutually exclusive events, because in this case, remember, some have both a dog and a cat. So the way we do that for non-mutually exclusive events is we take the probability of A or B is the probability of A plus the probability of B, as we did for the mutually exclusive event, but then we subtract the intersection, which is the probability that they will own both. So in this case, the probability of a cat or a dog equals the probability of a cat plus the probability of a dog minus the probability of having both a cat and a dog. And as you can see, the math, we have 0.25 plus 0.20 minus the 5% that own both. So the probability of either owning a cat or a dog comes out to 40%. When we were working with addition, we were trying to determine the probability of an either-or event. When we're working with multiplication, we're typically trying to find an AND event. So we're going to start with multiplication for independent events. Remember, an event is independent when one outcome has no effect on the other outcomes. So in this case, we're going to be using the example of tossing a coin. Tossing a coin and having it come up heads does not preclude it coming up from heads again. So in this case, what if we wanted to find out the probability of tossing a coin twice and having it come up heads both times? Well, the formula for that is the probability of A and B. In other words, A as heads and B as heads is the probability of A times the probability of B. So the probability of A being heads and B being heads is 0.5 times 0.5, or in this case, 0.25, or 25% probability of tossing a coin twice and having it come up heads both times. As long as our events are independent, it doesn't matter how many events are included in our experiment. So let's take another example. Let's assume that you're going to roll a die 3 times, and you want to know what the probability of having it come up as a 1 the first time, a 2 the second time, and a 3 the third time. Well, we just take the same multiplication formula. We take the probability of getting a 1 times the probability of getting a 2 times the probability of getting a 3. We have 1/6 times 1/6 times 1/6. We end up with a probability of getting a 1, 2, and a 3 as 0.00463. A dependent event is when one result does affect the chances of having another result come up. So for dependent events, we have the probability of an A and a B, and we'll explain this in the next slide here. But the probability of A and B is the probability of A and the probability of B given that. We use a little slash there for given that, because in this case, there is a probability of B being affected by the probability of A having already occurred. All right, here's an example to hopefully make this make a little bit more sense. So assume you have a bowl filled with 20 pieces of candy. 10 of those are blue and 10 of the pieces are yellow. And so we want to compute what is the probability of choosing 2 candies at random and having them both be blue. Well, obviously, choosing a blue candy the second time is affected by the fact that we took one out the first time. There's not as many blue ones in there. So here's the formula there. So we have the probability of blue the first time and blue the second time equals the probability of blue the first time times the probability of blue the second time, given that we've already taken a blue candy in our first try. So the first time, the probability of a blue is 10 out of 20. The second time, though, it's only 9 out of 19 because, again, one piece is missing and that piece is blue. So we multiply the two together and we have the probability of getting a blue piece both times of 0.23684. Now, the second blue outcome is a conditional probability. Conditional probability is the probability of a specific event occurring given that the other event, blue the first time, has already occurred. Well, as we're progressing in probability, we're getting a little bit more complex, and so we're going to briefly discuss contingency tables. So when we attempt to classify observations in 2 or more categories, we often create contingency tables. Contingency tables lay out the responses in a crosstab format with the number of responses in each of the different groupings. Computing probabilities in contingency tables uses the dependent events formula, which we talked about in the previous screen. So let's get an example here, and hopefully this will make sense here. So assume that you want to see if male students prefer different fast food locations than female students. So you ask the students to select their favorite fast food restaurants, but you've given them a set list of three. And so we're going to classify those results by male and female, and then how many selected each of the three choices of favorite fast food restaurants. And we'll see that in the next slide with a contingency table. So here we see the results of the fast food survey laid out in a contingency table that has rows for the genders and then columns for each of the three fast food choices. Now you'll see that we've totaled them up by choice, by gender, and then also a grand total. Now the value of 23 in the Chicken Deluxe field is dependent upon the gender being male. For instance, the value of 18 in the Burger Queen section is dependent upon the gender being female. The value of contingency tables is that they allow us to see the different values for each of the selections, and it's a little easier to actually compute probabilities once you get familiar with how these are laid out. So let's go ahead and answer a question here. What is the probability of finding a respondent in our survey who is female and prefers Burger Queen? So we use the dependent events formula, so the probability of A and B, in this case the gender being female and B being Burger Queen as the selected choice, is the probability of A, female, times the probability of Burger Queen given that the gender is female. So putting the numbers together here, we end up with 63 over 108. So we have 63 females in the survey, when there were a total of 108 individuals altogether, and then we multiply that by 18 of the 63 females who preferred Burger Queen. So 18 divided by 63 times 63 divided by 108 equals the probability of 0.1667. When we're conducting experiments for research, we often need to know how many possible outcomes can result. For example, if you toss a coin, there's only two possible outcomes. But what if you toss 3 dice? There are many more possible outcomes. Or you toss 3 coins. So in determining how many possible outcomes we have, there are 3 different methods and formulas we will use to do that. The first method of determining the number of possible outcomes is the multiplication formula. Now we use the multiplication formula when an experiment has multiple steps or a certain way of doing things. So for example, let's assume our experiment is rolling 2 6-sided dice. So the first dice has 6 possible outcomes, and so does the second. So using the very simple multiplication formula, we can determine that the number of possible outcomes is 6 times 6, or 36. The combination formula is another method, and it's a little bit more complex than the multiplication method, but the experiment is a little bit more complex. So let's assume that you have a list of 7 movies that you want to watch, and on a particularly boring weekend you've decided to watch 2 of those 7. So the combination formula allows us to determine how many ways those 2 movies, we designate that with an R, can be selected from the larger group of n. So you see the formula here, and I'll step us through how it's computed here in the next slide. On the screen here you can see how we actually compute the number of combinations available of watching 2 movies out of a group of 7. We of course use the factorial to do that, and this is showing you how to compute it longhand, and of course as you might have guessed, I'm going to get to an Excel method here in just a minute. But the total number of combinations of 2 out of 7 movies, watching 2 out of a group of 7, is 21. With the previous example using the combination formula, selecting 2 movies out of a group of 7, the order was not important at all. Now in situations where the order is important and we want to say, well, this one, then this one, then this one, we use the permutation formula. And I'll explain the permutation formula in the next screen here. So here we see the permutation formula, slightly different than the combination formula. And again, with our example of the movies, we're still going to watch two movies out of a group of seven, but we've specified that the order is important. In other words, maybe we want to watch one pair of movies before another pair. So with using the permutation formula, we end up with 42 possible combinations. All right, let's check your understanding just a bit here. So when we were using the combination formula, choosing two movies out of a group of seven, we ended up with a combination of total of 21. But when we used the permutations, we ended up with 42. Why is that? All right, permutations is the formula that we use when the order is important, and combinations is when it's not. So, for example, the pair of two movies that we chose with permutations, for example, we could watch movie A first and then movie B, or we could watch B first and then A. So the pairing of A, B, and BA are two different possible combinations using permutations. With a combination formula, the order isn't important, so selecting B and then A represent only one combination, and so that's why we end up with twice as many combinations with the permutations formula versus the combinations formula. That'll make much more sense here in the next example, I think, too. All right, here's another example. So let's assume that you locked your bike up and it has a combination lock with 4 digits on it, and those digits can be from 0 to 9. So how many 4-digit patterns are possible? And are we going to use the combination formula with the combination lock or the permutation formula? Well, hopefully you guessed that you would use the permutation formula because in this case the order is definitely important. First this one, then this one, then this one, and then this value. So using the permutation formula with n being 10, 10 possible digits, with r being 4 selections, the number of permutations possible is 5040. So you'll be there a long time trying to figure out what the correct combination is to open up your bicycle lock. Okay, let's try another one. You have 2 pairs of shoes, 3 pairs of pants, and 5 shirts. How many different outfits can you create from this wardrobe? Well, in this case, you use the multiplication formula. You multiply the 2 pairs of shoes times 3 pairs of pants times 5 shirts, and you end up with a total of 30 different outfit combinations that you can wear from what you've got hanging in your closet. And as I already mentioned, Excel does have formula functions for computing both combinations and permutations. You just need to know the number that you're choosing and the number available, and it will compute each of those, the combination or the permutation. Remember, we use the combination when the order is not important and permutations when the order is significant. Okay, let's do a quick review of what we talked about in Chapter 5, probability. Probability is the chance of something happening, or the odds of something happening, and the probability or the odds vary from 0 to 1 or 0% to 100%. When we're working with mutually exclusive events, when we want to compute the probability of an either or, the formula is the probability of A plus the probability of B. When the events are non-mutually exclusive, we have to consider the intersection between the two. So the probability of A or B would be the probability of A plus the probability of B, and we would subtract the intersection where both A and B are occurring. All right, we talked about multiplication for independent events, and the perfect example here is tossing a coin twice and having it come up heads both times. So that probability would be the probability of A, heads the first time, times the probability of B, heads the second time. If the events are dependent, which means the first event affects the outcome of the other one, we would take the probability of A times the probability of B given that A has already occurred. And when we want to determine how many possible outcomes we had 3 methods depending on what we're doing. We could use the multiplication method, which is simply outcome 1 times outcome 2. Or the combination method when we have several different items to choose from, and then we're going to select X number of items, or in this case, R number of items. We use the combination formula when the order is not important. When the order is important, we use the permutation formula. And remember, Excel has both the combination function and the permutation function, or you can do it longhand using the formulas you see here. And remember, all of these lessons are based on my textbook, Surviving Statistics, which is available on Amazon. And do remember to check out my website for downloadable files, calculators, and other resources.